Number 12?
Yeah.
On which one?
Uh,
The old exam?
yeah.
Can you read out the question?
Calculate the minimum number of jobs of 6.004 chemistry class results on the graph.
To dissolve how much?
1 gram of silver chloride.
So you want to dissolve 1 gram of silver chloride in 6 molar NH3. So how would you set this up? Or what did you start?
Combine stuff.
The combine? Yeah. We do the combine. As, we're looking at the solubility of silver chloride. So you have silver and chloride. And then the ammonia we know attacks what? The silver. So silver plus 2 ammonias will be given. It's a diamine complex. So this is the reaction we did in the lab. We just wanted to do a calculation, figure out. We didn't generate it by a full gram. We generated much, much less. If you had a full gram, what would it be? And so the combined method works because of why? Combined method works because well, in order for combined method to work, what,
There has to be a new K,
Yeah.
it has to be
the first one's small.
The
Small,
one
yeah.
and the other one has to be large.
yeah. The first one was what? 1.6 times 10 minus 10. 7 minus 10. There's a KSP for that.
Are you gonna give us the KSP? And
Yeah,
the K
KSPs
on
will
the-
be given on the test, so
Okay.
you don't have to.
I was just saying because it's not.
It's not on there? And I have to look it up. Unless, does somebody have it from their notes? Okay, 1.8 times 10 to the negative 10. KF is 1.6 times 10 to the 7? Alright. That's pretty big. To the positive 7. So then what?
KSP times KF.
Yeah, this is going to be KSP times KF, which we call KSPF, which is equal to 2.88 times 10 to the negative 3. All right, did we do this one in class? Does this one look familiar? Yeah, we did this one in class, so I could do it again, but if you missed that time or you don't have those notes, make sure you get them from somebody because this is sounding familiar, this one. So just register to this. And so here, basically what we did was we just set it up. You know, initial is 6.00 molar, 0 molar, 0 molar. And then, we calculate the solubility. Once you figure out the solubility, that's how many moles will dissolve in a liter. And so we have this many grams. This is a lot less than a mole. A mole is 143 grams. So this is a lot less than a mole. So we don't need a liter. We need a lot less than a liter to dissolve this. And so we just convert it from grams to moles, and then use the solubility to figure out how many liters. The solubility of silver chloride. And then we go to milliliters and then to drops. Did somebody have the answer for this? How many drops did you get?
I got 481.
481? Anybody else have the answer to that? Okay. Well, yeah, yours sounds good, Ron. Yeah, so that's how you do it. But take a look at your notes. If you don't have them, just get some notes from somebody else who has it. We worked it out, the entire problem.
For ions, complex ions,
Mm-hmm.
I thought we referred to the concentration as X, not S.
In this case, this is S. This is S because we look, where does all this come from? This is going to come from the silver chloride dissolving. And so this is the maximum amount of silver chloride that can dissolve here. And so this would be S. When we go from solid to aqueous, it's S. And so here, sometimes we get a 2S, but S is how many moles of silver chloride actually will dissolve. Not necessarily form silver chloride, it's going to form those species, but this is it. S and S. All right, other questions?
Oh, can you go to 11?
11? What was number 11? Can you read out the question?
Calculate the solubility of barium sulfate in water at pH of 2. I just want to see if I did it correctly.
Barium sulfate? Okay. Did we do that? Did we do barium sulfate as an example in class? That one sounds very familiar too, because I thought we probably did a different pH though.
It was the same pH.
It was the same pH we did in class? If you don't have the notes for that, just get it from somebody, check it. Well, since we're talking about chapter 18, there's one thing I want to say, and I wasn't sure I was going to mention this because, for the advanced integrated problems, let me just mention something here. Let's Let's take a look at number 82. This is a question I got in the afternoon class, but I didn't mention it in the morning class. Anybody do number 82? Yeah? Okay. Anybody look at the book, the solutions manual for number 82? Did the solutions manual make sense for number 82? Not really, yeah. The thing about number 82 is when you look at number 82, we want to use the combined method for this as well. I mean, it's PbCl2 solid. It's going to give us Pb2 plus 2 chlorides. And then the Pb2 plus can be complex, right? 3 chlorides. It's going to form PbCl3 minus. Like this. And for the combined method to work, KSP's got to be what? Small. But, you know, when you look at PbCl2, you look at the KSP, have you guys looked at the KSP chart and just looked at it? Let's take a look at the KSP chart. Have you looked at the biggest KSP and the smallest KSP? No? So you have no idea what the range of KSPs are then. Somebody asked you, what the typical range of the KSPs are. That's it's like important because let's say you're studying forests or something like that. And somebody asks you, hey, what's the biggest tree in your forest? What's the smallest tree? And you say, I don't know, because I never bothered looking at the biggest or the smallest tree. What's the range in the size? What's the tallest tree? I was on the internet the other day. I saw, the tallest tree in Texas. That's interesting. What is the tallest tree? How tall is that tallest tree in Texas? Right? No idea. Then I realized, wow, there are actually people who take these tours and they go visit, all the trees, the tallest tree, the tree with the biggest circumference, etc. But what I find with most people with the charts, and this is why I said at the beginning of class, if you look at the charts, you're already one step ahead of most other people because most other people don't look at the charts. They don't care what the biggest or the smallest value is. They just want to find their number and that's it. But PbCl2, we look at this chart and there's a pretty big range. One thing about this is, this is something only, if you have the luxury of time, If you have the luxury of time, then you can notice all kinds of little connections or whatever else that other people might not have noticed before. And this is, I was watching some other TV documentary. Did I tell you about that Roman thing I was watching? About agriculture, how agriculture, that gave them the luxury of time to look at a lot of other things. And what they figured out were some really useful chemical reactions that they were able to do, and that is to make concrete. Concrete, it's a huge advance in architectural material, structural material. And even concrete nowadays, people are studying concrete. When I was at UCSB, we were collaborating, our group was collaborating with the Navy at Point Magoo. And what the Navy wanted to do was they wanted to make a more resistant concrete because the concrete that they had, was exposed to the ocean environment, and they had weathering issues, they had erosion issues, and a whole bunch of stuff. So they wanted to formulate a new structure for their concrete to make it more resistant to weathering and erosion. But that helps not just the Navy, but it helps everybody to do that. And so that was a very interesting project, and looking at how to characterize the structure of that concrete. But going back to this, when you have luxury time, then you'll start to notice some strange things on this table. For example, the solubility rules. Does this jibe with the solubility rules, this chart? And so one of the things you'll notice is like lithium. Hey, lithium salts are supposed to be soluble, but there are a bunch here. Lithium carbonate, lithium fluoride, lithium phosphate, group 1 salts is supposed to be soluble, right? But it looks like lithium is an exception. Do you see any sodium, potassium on here? No, so there are a lot more exceptions with lithium, okay? Well, then we have to be careful when we're dealing with lithium salts, but that makes sense because lithium is a very, what? Lithium is a very, a very small ion. It is a very reactive metal, but the ion itself, lithium ion is very unreactive. If you look at lithium ion has the reputation of being the worst oxidizer on the chart, right? Lithium ion. But as far as metathesis goes, it's pretty reactive metathesis-wise, as you'd expect, because lithium ion, being small, will form strong electrical interactions with other species. So you see lithium, and then it depends if you have lots of time. If you have lots of time, then you look. Chlorides are all insoluble except for silver. Okay, that makes sense. Silver is 10 to the minus 10, right? Silver chloride. Mercury 1. Mercury 1. 10 to the minus 18. Wow, mercury 1 is quite a bit less soluble than silver. And then lead. When you look at lead, it's 10 to the minus 5. 10 to the minus 5, where does that rank it? Well, 10 to the minus 5, is fairly on the more soluble end of things. I mean, let's take a look at things we expect to be soluble, like, for example, calcium hydroxide. Let's see, is calcium hydroxide here? Yeah, calcium hydroxide. It's kind of weird because we say that hydroxides are all soluble except for group 1, ammonium, calcium, strontium, barium. So calcium hydroxide is actually a soluble hydroxide. That has a KSP of 10 to the minus 6. But, this splits differently, so, that would be the cube root of that. But still, and then we look at lead-2 chloride. Well, lead-2 chloride splits in the same way. That has a solubility of 10 to the minus 5. 10 to the minus 5 is, versus 10 to the minus 6. 10 to the minus 6 is actually smaller, right? And we call calcium hydroxide soluble. Maybe we should stop calling it soluble, But it could be other issues too, hydroxide, hydrolyzing, whatever else is in there, maybe CO2. People, sometimes you get into this, and you learn that, and you memorize that, and then all of a sudden somebody confronts you and says, hey, wait a minute, why are you saying that? I mean, is that wrong? And so once in a while you look at this, and then see. But what it turns out, and you don't probably have experience with this, but lead-2 chloride is fairly soluble, 10 to the minus 5. It's like borderline. And so you get, and so in this case it doesn't, starting to get on the more soluble end of things. This combined method works great if it's like 10 to the minus 38 or 10 to the minus 50. There's 10 to the minus 50, isn't there? There's 10 to the minus 50 on here? 10 to the minus 53. If it's like that, wow, this combined method is going to work fantastic because that means there's going to be very little free ion, right? But when you get to like 10 to the minus 5, right? 10 to the minus 5, what else is there bigger? 10 to the minus 4, and then these lithium ones are fairly soluble, 10 to the minus 2, 10 to the minus 3, They're borderline soluble. Then we start to worry a little bit that there's going to be more free ion. And so maybe the combined isn't going to work as well. When we look at the range of KSPs, we want it on the smaller end, 10 to the minus 20, 10 to the minus 30, 10 to the minus 40, 10 to the minus 50, it will work fantastic. When we get to the bigger end, the bigger end is below 10 to the minus 10, 10 to the minus 5, then we start to worry a little bit that the combined method might not be the most valid. It's like when you use the ideal gas law. When you use the ideal gas law and you're dealing with 100 atmospheres, do you think it's going to give you a pretty accurate calculation? 100 atmospheres, gases are going to probably start deviating significantly from ideal behavior. If you use it at 1 atmosphere, it's probably fine because most gases behave ideally at 1 atmosphere, so no problem. And so it's the same kind of thing. In the back of our mind, we start to worry that, you know, our assumption might not be so good. Well, hopefully KF is big. If KF is big, then that'll take care of it because KF will scoop up all the lead ions out of there. So let's take a look at the KFs. Have you looked at the KF table? Because this is what I'm saying. You know, what I'm saying is, okay, it's one thing to say small KSP, big KF. It's another thing if somebody says, well, what is a small KSP? And then what do you say? Well, I don't know because I don't know any numbers, right? It just has to be small, whatever that means, you know? And then the big KF, what does the big KF mean? Well, big KF means, let's see what the KF is, wrong direction here. Well, what are some big KFs? I mean, we saw some big KFs, 10 to the 33, 10 to the 42, you know, there's some big KFs, okay? So if it's a big KF, like 10 to the 42, then we're happy. 10 to the 37, you know, we did that one, 10 to the 37th, that's pretty good. Or, yeah, that was one of the calculations we did earlier, 10 to the 37. And so that works out nicely. But what are some of the smaller KF there on the chart? 10 to the 1, oh yeah, 10 to the 1 is not so big in the relative sense of things, right? And so on this side, this is approaching the time where we start to worry. We start to worry that the combined method might not work so well. But you know, how do we know? Do we have like this thing, or you know, we calculate the percent, whatever? Well, we don't. Otherwise, how are we gonna solve this? Because if we don't solve it using the combined method, we must solve it using the simultaneous method, which we could do. We could try to solve this simultaneously, right? But, you know, it's not like the previous chapters where there's a simple check, okay? The simple check, you just look, did it perturb the previous step, you know? I guess we could do it. We could do that. We could do a simple check. This would be step 1, and then step 2. We could try it stepwise. You know, combined fails, try it stepwise. Stepwise perturbs, then we got to do it simultaneous, right? But anyway, nonetheless, you know, we aren't getting too advanced. We don't want to get too advanced. We just want to solve this. And so what we're going to do is we're going to solve it using the combined method, but we're going to say maybe our calculations are going to be off, right? That's it. But go ahead and you solve this using some combined. Did anybody solve this using the combined method, or did everybody solve this? You didn't use the combined method? Did you use the solutions manual method? Well, set it up using the combined. Can you set it up and solve the solubility? Let me grab the solution. I'll show you. You know, it's hard to find books without errors in them. You know, we've never used a textbook that didn't have errors in there. Document. Okay, one thing the book, that I don't like, the book never uses the ice tables, no? I can understand why, because if they set up ice tables, it just takes up a lot of room. All right. So number 82, actually, we probably should read the question first. As you don't look at it. Let's read the question for number 82. Use KSP for PbCl2 and KF for PbCl3 to determine the molar solubility of PbCl2 and 0.10 molar HCl. So this is the way I would have set it up. 0.10 molar HCl, is that initial chloride or equilibrium chloride? HCl is just going to give us chloride. Initial or equilibrium? Initial. It says in 0.10 molar, and that means PbCl3 should be 0 molar. Right? So here, okay, in 0.10, hint, what is the total concentration of lead? I gave you that hint in Visual Mintech. Do you remember? I said the total lead concentration would be the sum of all the lead-containing species. Well, here, we don't need that hint because all the lead that dissolves from lead-2 chloride ends up in PbCl3 minus because we're assuming that the Pb2 plus is negligible, right? Because KSP is small, generates very little, KF's big, and eats it up. And so this should be minus S plus S. And so we end up with 0.10 minus S, and then S. And so the KSPF is going to be equal to, okay, thank you. Now let's see what the solution manual did. The first thing we noticed is the solutions manual didn't do combine. You know, the solutions manual did this. They did the KSP, so we take PbCl2 solid, and then we go to Pb2 plus and 2 Cl minuses. Right? And then they didn't set up the ice table either, but let's set up the ice table, right? Because that's what we do. We set up the ice table. Now, is the chloride initial or equilibrium? The chloride. Initial, right? This is a common ion problem. So 0.10 molar initial, 0 molar here. Having common ion here means the solubility is going to be smaller. It's a common ion effect. So this is going to be plus S molar, and so at equilibrium we have S molar and 0.10 plus S molar. Is that correct? And so KSP should equal the lead concentration times the chloride ion concentration squared, which is going to be S times 0.10 plus S squared. Right? So what are they doing here?
They're just using KSP. They're putting the initial concentration of Cl instead of 3.10.
All right, all right. So what they did was they didn't say we were starting off with this. What they're saying is how much Pb2 plus can we have, right? Okay, so let's take a look. They're just, what they're saying is they're doing this. They're saying here, if we have this initial change equilibrium, they're going to just say at equilibrium I'm going to have 0.10 molar chloride. Therefore, you know, how much lead can I have in here? And so they're calculating the lead concentration at equilibrium here. So lead concentration at equilibrium is just going to be the KSP divided by 0.10 squared. Okay. They come up with 1.6 times 10 to the minus 3 molar. All right. What was the question again? What were they asking?
find the solubility of.
Find the
lead to-
solubility.
Of lead to
Okay.
chloride on 10 hydrocarbon.
Find the solubility of, that means no lead has dissolved. No lead 2 chloride has dissolved yet, right? No lead 2 chloride has dissolved yet. All right, now, have you ever heard the term mass balance? If you read Visual Mintac, then you would have heard the term mass balance if you read the whole literature. Because mass balance is how they solve those simultaneous equilibria. Mass balance means, very simply, that not equations, but atoms can neither be created nor destroyed, right? That's all. It's the conservation of mass. Well, here I have one violation of the conservation of mass, right? Because where did all this lead come from? If we have 1.6 times 10 minus 3 molar lead ion, that lead ion came from lead 2 chloride. So for every mole of lead 2 chloride that dissolves, how many moles of chloride do we get? We're going to get twice as much. So we should have gotten 3.2 times 10 to the minus 3 molar chloride. If this much lead formed from lead 2 chloride, then we need to have 3.2 times 10 to the minus 3 molar chloride in addition to that. Otherwise, this is, you have lead 2 chloride and it dissolves. When it dissolves, it forms 1 lead ion and 2 chloride ions. Well, when I look at this equation, this equation saying, okay, I don't want the chlorides, just give me the lead. Can you take the lead without the chloride? No, oh, you know what? Chlorides can stay in the crystal lattice. Okay, just leave the chlorides in the lattice, just give me the lead. Can you have PbCl with a little bit of extra chloride in there? A lot of extra chloride? Actually, a lot of extra chloride. In other words, I want to make water. I have hydrogen, I don't have any oxygen. So I'm going to make water with hydrogen and no oxygen. Is that possible? That would be a violation of mass balance, right? Likewise, I want to decompose water into hydrogen, but I don't want the oxygen. Just give me the hydrogen, you keep the oxygen. Is that possible? That's a violation of mass balance. Well, this is a violation of mass balance. Do you see it's a violation of mass balance? Because where's that extra chloride? Where did the extra chloride go? The extra chloride just disappeared. Because the 0.1, where did that 0.1 come from? That came from the HCl, so that's accounted for. But what happened to the extra chloride? It disappeared. That's a violation of mass balance. So, well, you could say maybe they did this. Maybe they said, that extra chloride 3.2 times 10 to the minus 3 is negligible. But it's not really negligible here because it's like 3.2%, right? If this is 0.100, then it's 0.03. Is that negligible? To say 3% is negligible? No. All right, what's the next issue that came up? Well, the next issue is, okay, then they did what? They took the Pb2 plus and then went 3 chlorides to form PbCl3. All right, now what are they doing here? Let's take a look because, we like to set up the ice table. So we'll just go ahead and set that up. But they're saying that at we're going to have lead at 1.6 times 10 minus 3. So lead is at 1.6 times 10 minus 3 initially or at equilibrium? This is one of the reasons why I wasn't even going to talk about this is because very few people actually do the advanced actually do the advanced problems, and then a small percentage really. Let's see. So sometimes I'll talk about these errors. A lot of times I'll just skip them because. But that is at equilibrium or initial. That's equilibrium. So this is 1.6 times 10 to the minus 3 molar at equilibrium. Now the chloride is at at equilibrium or initial? At equilibrium, 0.10. And then they're calculating this, the equilibrium concentration PbCl3. So they calculate the equilibrium concentration PbCl3 minus. So PbCl3 minus, this is equal to 3.8 times 10 to the minus 5 molar. Well, this is simultaneous because, right, hey, this is simultaneous because they got the same chloride in both equilibria, right? And they have the same lead. So if you have the same chloride and the same lead, hey, it doesn't perturb. So this is our step 1, this is our step 2. Actually, they did stepwise, not simultaneous, right? But essentially, it's kind of like simultaneous because they said, well, we have to solve this simultaneously, therefore the lead in the 2 equilibria must match, and the chlorides in the 2 equilibria must match, and they do. Do you see it? It matches. So, hey, this is the easiest way of doing simultaneous equilibria, isn't it? It's
But for this one, wouldn't you do simplifying assumption? Wouldn't it still calculate to be the same?
Yeah, it would still calculate to be the same, but when we do the addition, we can't ignore it. Even though we use the simplifying assumption to calculate S, we still add the S to the 0.1. And so this concentration comes out to 0.103, right? Or what was it? S, not 103, 1016. This concentration comes out to 0.1016 squared, and then this is 0.0016. And then we multiply it. We don't do 0.0016 and then 0.10. You know, even though we use a simplifying assumption, we still factor that in. Because if we did this, then we're going to be way off. Our KSP is going to be way off. Well, not way off, but it's going to be off. I mean, the K value. Well, anyway, going to this. Do you see, they did it, and the leads match, because this is 1.6 times 10 to the minus 3. That's 1.6 times 10 to the minus 3, and then the 0.1 molar, 10 molars match. Well, that was the whole point of doing simultaneous. So the whole point of doing simultaneous is that the concentrations have to match the common species, right? And they did it. Boy, they did it, and it was easy. Compared to, remember the simultaneous we set up? That was hard. But they did it, and it was easy, right? But there's a question about this, and that is, wait a minute. You know, if this is 3.8 times 10 to the minus 5, I have a couple of issues with that. If this is 3.8 times 10 to the minus 5 molar, where did the chloride for this come from? Because if that's 3.8 times 10 to the minus 5 molar, then for every one of these, I need 3 chlorides to attach to it. But we only had 0.10 molar chloride to begin with. And so where did the extra chloride come for this? Well, maybe that extra chloride was over here. Remember, we lost some chloride over here. We lost, we needed another 3.2 times 10 to the minus 3 molar chloride, because for every 1.6 leads, we need double that amount in chloride, right? And this 0.10 came from the HCl, so maybe that's it, but no, it isn't, because if we have 3.8 times 10 to the minus 5, we need 3 times that in chloride. So what's 3 times 3.8? About 12. 2 times 10 to the minus 4. And so in other words, this. Where did the chloride come for this? Can you tell me? Well, it's going to be 3, let's say that's 4. So 3 times 4 is 12. 12 times 10 to the minus 5. Hey, I had some, that's 10 to the minus 5. I have some extra left over here. So I could use that. But if I have extra left over here, what happens to the unused portion? And so anyway, the chlorides don't match. And then the other question is, hey, where did that lead come from? This lead I know came from PbCl2. Where did this lead come from? So, anyway, basically, this is it. There's a serious problem with this. The serious problem is that the atoms don't balance. It's not balanced. These don't balance. And so in other words, they're creating atoms when they need it, and they're destroying atoms when they don't need them. And so this is a violation of mass balance. You can't solve it this way. Okay. Why did they do this? And so anyway, the solubility of lead is 1.6 times 10 to the minus 3. Well, here, this is negligible, I guess you could say. And so if we ignore it, that's still a problem with mass balance. Okay. We should solve this simultaneously. All right, that's why maybe I shouldn't spend time. I wasn't going to talk about this. But what we did, we did it, since we did this one in the computer lab, we did this in the computer lab, right? And when we do this in the computer lab, then we add up all the lead-containing species, which there are more than this, and then that gives us the total solubility. So you can compare it with what we did in the computer lab. Okay. All right, any other questions? Chapter 18? Maybe neither is so accurate, maybe, I don't know. Okay, we're going to continue with chapter 14 now. All right, chapter 14, the chemical kinetics. 14 through 1. 14.1 through 14.7 deal with the empirical equations from kinetics. Empirical equations we get when we have multiple reactants. Just a quick review. When we have multiple reactants, AA plus BB plus dot dot dot, this goes to product. Then what are the equations that we generate from this? The only equation that we generate from this is that the rate is equal to Ka to the M, B to the N, etc. And so we have this equation. This is rate law. This just tells us how fast the reaction occurs at different concentrations. And that's basically all we're going to get. Now, is that very useful? Well, it depends. You know, the rate is just equal to 1 over A, delta A, concentration over delta T, etc. Not so much. What we want to know is how long it takes. But the problem with how long is that when you look at the delta A here and the delta T here, what's the problem? You know, if I wanted how long, then I just look at the delta T or the time interval. If I want to know how much reaction takes place, I look at the delta A, but we can't use this delta A and delta T to do calculations here because delta A and delta T are changing, always changing. And so that's a problem. Well, in order to figure out how long and how much, you know, to figure these out, then we need to use calculus. We get something called the integrated rate law. But using calculus and integrated rate law for multiple reactants is difficult. And so we go to single reactants. Single reactants would just be AA goes to product. Or pseudo single reactants. You know, pseudo single reactants would be something like this, where we can get it to look like it. And so if we had AA plus BB plus CC goes to product, what we do is we make, you know, 2 of these very large concentrations. That means they're fairly constant, which means that the rate law is going to simplify into this. Rate is going to equal K, A to the M, B to the N, C to the O. If we make these constant, then we can just blend those into K. And so we end up with K prime. This is what K prime A to the M. And so over here, you know, if we just have a single reactant, then rate is only going to depend on that single reactant, Ka to the M. So in this case, we can get that. When we have something like this, then we can determine, you know, how long and how much by using the integrated rate law. And so there are going to be 3 scenarios that we're going to have. We're going to have 0 order. 0 order, the half-life does what? In the 0 order reaction, the half-life decreases each successive time. And so we see the T1 half gets smaller each time. Right? So the first half-life's that. The second half-life would be 1/2, T1 half, etc. And so the half-life just gets cut down each successive time. So the first, second, etc. The plot of concentration of A versus T is linear, with the slope of this related to K. In fact, K is just the negative of the slope of this, so we just change the sign. And so if it's 0 order, then the rate is equal to Ka to the 0. That is, the change in concentration doesn't change the slope, so it's just equal to K. The slope. And the integrated rate law that we can get from this is that the concentration of A at time t is equal to minus Kt plus the concentration of A at time 0. 0 order. So there are different ways of figuring out if it's 0 order. You know, we can graph it, etc. If it's first order, with first order, T1/2 is constant. So sometimes it's easier to talk about half-lives rather than rate constants. You know, rate constants are a little bit abstract. But for first order, the easiest thing to do is to talk about characterizing that reaction in terms of half-life. And in terms of half-life, let's take a look at how they vary. Some reactions are very fast, so they have an extremely short half-life. And some reactions are extremely slow, and they have very long half-lives. And so we can take a look at a table of half-lives here and see how they vary. When we do a plot of A versus time is going to be nonlinear, you know, and we could recognize it based on this half-life trend. See, this exponential curve. But if we do a plot of the natural log of the concentration versus time, that comes out linear, and this K for this is equal to the negative slope. Here again. The rate law is just rate is equal to Ka to the first. And then the integrated rate laws, given as ln of A at time t over A at time 0 is equal to minus kt. Now these equations you don't have to memorize. I'm just going to give them to you. And so ln of A, you just have to know when to use them. ln of A at time t is equal to minus kt plus ln of A at time 0, using the property of logs. For this, you know, since the half-life is constant, it's kind of easy to come up with it. The half-life is equal to 0.693 over K. We solved this equation earlier. So we can interconvert between half-life and K. So let's take a look at some half-lives here. Here you can see how the half-life stays constant, it's fixed. So you can recognize the curve for that particular reaction. And so here's some half-lives here. Like your radioactive, all radioactive decay processes turn out to be first order. And so U-238 decays 4.5 billion years. There's carbon-14 is 5,730 years. Phosphorus 32 is 14.3 days half-life. Iodine-131 is 8 days half-life. Iodine-131, 8-day half-life, you know, they're fairly short. Sucrose, you know, sucrose, this is called hydrolysis sucrose, 8.4 hours is a half-life. But if you add a catalyst to this, it's very quick, etc. All right. So that's first order, and then we have second order. So second order, the half-life doubles each time. So the first half-life is T1/2. The second half-life is going to be 2 times T1/2. And so if the half-life's doubling, then it's easy to draw the curve. You know, you just figure out, okay, the first half-life's here. Second half-life's going to be twice as long, guesstimated here. And so the curve is going to flatten out quite quickly. The next half-life's going to be double that, the previous one, so it's out here. So it's easy to draw the curve. It's easy to recognize the curve if you see something like this, where this has to be single reactant. You know, it can't be multiple reactants, because if it's multiple reactants, then everything's going to have an impact on the curve. And so if we can isolate it to a single reactant, then we know, oh, this is going to be second order. Rate is equal to Ka squared. And if we make a plot, because if we make a plot of 1 over A versus time, it comes out linear with positive slope. Slope is equal to k. If we make a plot of ln of a versus time, it's nonlinear. That's from the integrated rate law. The integrated rate law is 1 over 8 times t is equal to kt plus 1 over 8 times 0. So these are the equations we use. So we can do calculations. We can calculate the delta t's. You know, delta t is just the time interval t, or we can calculate the change in concentrations, which is, you know, a0 to at, and do all those calculations. But the restriction here has got to be single reactant, which is kind of restricted, but it's all right. So that's the first half of this chapter. The second half of this chapter gets into the theory, you know, and so let's look into the theory of the rate law and where it comes from. So here's the summary here of this. I didn't write the equations for the half-life for zero order. You know, it's 1/2, and then there's the whole for the second order, but these are the equations. Okay, when we go to the theory part, we're looking at, you know, what's the origin? Here you can see, what order is it based on? The curve here. Let's see quickly. Maybe we can see it by the half-life. You know, if we look at the half-life, you know, this looks like second order, right? You can see it from the first curve. But you can see it here. This is nonlinear, nonlinear, this is linear, this has got to be second order. Okay, we're going on to the second part of this. Oops. The second part of this deals with where does this rate law come from? And so how can I determine these things theoretically? So let's take a look here. So basically, let's talk about theory here. So I have this rate law, you know, how fast the reaction occurs. And this is equal to K, A, to the M, B, to the N, etc. And so the first thing is K, you know, how can I determine that theoretically? And so what is the origin of K? And then M and N, you know, what is the origin of these? And so the first thing we think about is when a chemical reaction occurs, you know, a collision happens. And so the origin of these things are going to be based on these collisions that happen between reactant molecules. And so we call this collision theory, or just, you know, collision theory. And so we're going to look at, you know, how collisions will impact the rate reaction. So let's take a look at some collisions here. We'll start off with a simple collision here between two molecules. So we're going to skip this right now. I'm going to skip this. We'll look at something like this. Except I'm going to do a different example. Let's look at an example like this. A2 plus B2 yields AB. I'm going to need two ABs for that. I'm going to do just a simpler one than what they show here. And in a collision theory, let's say these are all gases. This is gas, this is gas, and this is gas. And so I have a molecule A2, represented like this. And then I'll have a molecule of B2, so I'll represent like this. And let's say they're moving at each other. When they move at each other, then they're going to collide. And in the collision process, what happens is bonds are broken and bonds are formed. And so let's say this. This is going to be called a reaction profile. It's shown there. Reaction profile, what it does is it just charts the progress of the reaction in terms of where it is in relative sense, that is kind of a time sense versus energy. And so in a reaction profile, we plot energy on the y-axis and charts the progress of the reaction. And so these are heading at each other, they're going to collide. Well, in the collision, the energy is going to go up, this. And so at the top of this, what we see is we see that the AA bond is starting to break. Let's break that. And the BB bond is starting to break. And in that process, the AB bond is starting to form here. And so what we have is we have bonds are being broken, bonds are being formed. This is not stable, right? This is just what we call a transition state. Transition state here. This is a high energy state in which the bonds are being broken, bonds are being formed. Now it has two choices. It could fall backwards. If it falls backwards, then the AA reforms and the BB bond reforms. We're left with what we started with. Or it could fall forward. If it falls forward, let's go, we're going to make this exothermic. Then it turns out we're going to form two ABs, an AB here and an AB here. So we completely break the AA bond and completely break the AB bond. So net, this would be an exothermic reaction here. The exothermic reaction is, it's a state function. So do you remember the whole deal about state functions? State functions only depend on the initial and the final state. They don't depend on how they got there. And so even though this looks highly exothermic, which it is, initially this is highly exothermic. But in terms of us, if this is the enthalpy here, what we say is this is a net exothermic reaction. And so here, delta H is less than 0. Because the products are more stable in terms of energy than reactants. But there was this big hump that we had to climb over, so it wasn't all exothermic. It wasn't just a straight downhill ride, was it? Initially what had to happen was there had to be a violent collision, right? And this violent collision had to result in creating this high energy transition state. And so what is this energy that it had to climb over, this peak? You know, once it gets to the top of this peak, then it's a long downhill ride. And so it's going to release more energy than it consumes initially. But this peak is going to have an energy called the activation energy. So the speed of the reaction, you know, is going to depend, you know, on how big this peak is to climb. You know, if your activation energy is very large, then, you know, how many molecules, what's the population of molecules that can climb such a large hill? You know, if the activation energy is very small, then the population of molecules that can overcome that barrier is very large. And so we have to look at the population, energy population of molecules at 25 degrees C. And so, you know, let's take a look at that. And that's something called, do you recall the name of this kind of curve? You know?
Bell.
Hmm?
Is it a bell curve?
No, it's not a bell curve. It's this curve here. It's kind of like a bell curve, but it's not symmetric. It's asymmetric. It looks like a bell curve, but it has this tail on it. It's a high energy tail. This curve is called, not a bell, but it's called a thermal distribution curve, or maybe it's called a, I call it a Maxwell-Boltzmann curve. Have you heard that term? Maxwell-Boltzmann. It's a distribution. It's another shape, Maxwell-Boltzmann distribution. That's the name of the curve. And so this black line is E sub A. This is that hill that has to be overcome. So this black line is this hill, and it depends on how big the hill is. The bigger the hill, the higher energy it is. The smaller the hill, the lower the energy is. So if it's a small hill like this, then the large population can overcome it, right? Because this is a population distribution. And so let's look at room temperature, T1 here. Room temperature is T1. This is kind of a high barrier. A very small population can overcome this, the blue here. And so when we're thinking about kinetics, we got to think about, how big is the activation barrier? Because that's going to dictate how fast that reaction can occur. Because the bulk of the molecules don't have sufficient energy, and the bulk of them don't, because if you look at it, the bulk of them will be under this blue line here. The reaction is going to occur slowly. It's going to give us this blue region here. If the activation energy is small, then the reaction is going to be a lot faster, as you'd expect. But there's another way to increase the population. The other way of increasing the population is via temperature. And so if we increase the temperature, right, we can increase the population. So at T2 is greater than T1, we see the population increases because what we do, we have the same population, so the area under the curve is the same. We just flatten it out some, increase the higher energy population. And so we need to know the mathematics of the Maxwell-Boltzmann curve. Do you recognize the mathematical equation that would define this curve? What kind of curve is that? Do you recognize this curve? This is a common curve in chemistry, a common curve. So basically what we're looking at here is the population versus the energy here, kinetic energy. Kinetic energy is given by Petrucci's E sub K. And then we have this bar, E sub A here. This is population. And above this bar are the population of molecules that can overcome that hump. And so the mathematics that define this is an exponential function, actually. And the mathematics that define this, it's like this. And when we look at the rate is equal to K, A to the M, B to the N. Now K is how fast that reaction occurs. That's the rate constant. The bigger the rate constant, the faster the reaction. The smaller the rate constant, the slower the reaction. Right? And so what does the rate constant depend on in theory? Well, the rate constant is going to depend on this. It's going to depend on two factors. The first one is A. This is a different A. This is called the frequency factor we'll talk about. And then it's going to depend on E to the minus E sub A over RT. This E to the minus E sub A over RT, this is just comes from theory. This one is this curve here, what is that population? And so this is how we see that population can change. One, it's going to change based on temperature. So the higher the temperature, the bigger the population. So if I increase the temperature, I'm going to flatten this out. This will be T2, this will be T1, T2 is greater than T1. And so the higher the temperature, the bigger the population. So this is inverted. So it's funny when you look at the math. And the lower the activation energy, and the smaller the activation energy, the bigger the population, the higher the rate. And so this term, this mathematical term, takes care of this curve, the Maxwell-Boltzmann distribution curve. Now, what's this other thing in front here? This other thing that's in front here, A, this is called the frequency factor. The frequency factor talks about, how probable is that collision. So we don't have much time. And so this is a perfect collision. An A collides with a B like this. But how often do we have a perfect collision like this? These things are moving in random. They have random orientations and we're moving in random directions. And so even if something has sufficient energy, let's say we have two molecules, there's plenty of energy to overcome the activation hump. Plenty of energy to overcome the activation hump, but let's say they're moving like this. A is moving in this direction, but let's say B is moving in this direction. Is that going to be a good collision? You know, and so by the time they collide, like this, by the time they collide, let's say they just so happen to collide, are we going to have nice bond breakage and bond formation? Is this going to yield the proper transition state? No. And so what this one does is orientation's wrong for reaction because we cannot form the transition state. Orientation is wrong for reaction. So even if we have enough energy in the wrong orientation, nothing's going to happen. And so most collisions don't result in any reaction at all because let's say we have it not, you know, side on. Let's say we have them coming head on. Is this going to result in two ABs? No. And so most of the collisions are going to not give us any product. It's only a small fraction of collisions that have the proper orientation to react. And so it depends on, you know, the complexity of the molecule, because some molecules are pretty simple. They're spherical in shape, and if they're spherical in shape, then it doesn't really have any orientation. You know, they have that symmetry. Whereas other molecules, they have some particular shape, and that shape really dictates the proper orientation for reaction. So the frequency factor can be big, it can be small, depending on, you know, how probable that collision is, the correct oriented collision, correctly oriented collision. And so it turns out that the rate constants can depend on these things, you know, the orientation and the population of molecules with adequate energy to overcome, and how, you know, the activation energy. Things that have a high activation energy have strong bonds. You know, things that have a low activation energy have weak bonds. So the stronger the bonds, the more energy it's going to take to break them. All right, and so that, you know, here you can see some more examples of favorable collisions and unfavorable collisions. You know, the orientation, these have to collide head on, and it has to be an oxygen colliding with nitrogen for proper reaction. But if we have two oxygens colliding, even with sufficient energy, nothing's going to happen, they just bounce off. The same thing here with the nitrogens, two nitrogens colliding. And then we can have angular, you know, collisions, you know, that don't result in it. And the reason we need the proper orientation is because of the transition state here. This is showing the transition state in which the bonds are forming here. They don't really show the bonds breaking, but the bonds are breaking at the same time. Those are forming, and then we result in products there. Continue on here. And so we have this. So this is just another reaction here. This is net exothermic, so we got a collision. We have this activation energy. You can see the activation energy here is 209 kilojoules. But overall, this reaction is exothermic at minus 139 kilojoules. So even though we have a big hump to climb over, in fact, the hump is bigger than this. Look at that, that's minus 139. Pretty big hump to climb over to get the product. But it's exothermic overall. Now, here, going forward, this is 209, but going backwards here, let's say these were to collide and try to go reverse, that's an even bigger hump, 348. So that reverse reaction will be happening. All right, now let's take a look at let's take a look at the concentration. And so here's some more stuff. Actually, temperature. We'll just go with this. Now, how does temperature influence this? We could use this equation as is, but you know, how do we get the numbers like A? You know, how do we determine that? And so let's look at this and doing calculations with this here. Actually, do we have time? We don't have time, so I'm out of time here. We'll look at